All right, today we're going to look at electricity in a totally new way. Forget just thinking about forces like pushes and pulls. Instead, I want you to imagine an invisible, energetic landscape all around us, a world of electric hills and valleys that, once you learn to see it, you can learn to map and, even better, harness for its power.
So let's just dive right in by reframing how we even think about this stuff. We're going to move past just thinking about pushes and pulls and into this much richer world of energy. You know, we're all taught that positive and negative charges attract or repel each other, right? That's the language of forces. But what if we thought about it more like gravity? We know an object has potential energy just because it's sitting high up on a shelf. It's in a gravitational landscape. So what if electric charges work the exact same way?
Okay, so the first piece of the puzzle is this thing called electrostatic potential energy, and really it's just a fancy term for stored energy. The official definition talks about the work done to bring a charge into an electric field, but let's just stick with our analogy. Think about how much effort it takes to push a heavy ball up a steep hill. The higher you push it, the more potential energy it has. It's the exact same idea when you're trying to shove a positive charge closer to another positive charge.
And this is where things get really clever. Instead of having to calculate the energy for every single different charge we might place somewhere, we can just describe the landscape itself. And that's exactly what potential, or what we commonly call voltage, is. It's just the potential energy per unit of charge. It's like looking at a topographical map and saying, hey, this point right here is 100 feet high. It doesn't matter if you put a pebble there or a giant boulder, the height of that spot is still 100 feet. Voltage just tells us the electric height of any point in space.
Okay, so we've got this idea of an electric landscape with different heights. So what's next? Well, we need a map, right? We need to figure out how to actually draw a map of it. And this graph here, it shows us exactly what that landscape looks like, around a single lonely positive charge. Just imagine that charge is the very peak of a mountain. Right near the top, the slope is super steep. That means there's a high potential. But as you move farther away, the hill gets gentler and gentler. Just like the graph shows the potential, V, dropping off as the distance, R, gets bigger.
Now, any good map needs contour lines, right? Those lines that connect all the points that have the same altitude. Well, in our electric landscape, we call these equal potential surfaces. Equal potential literally just means equal potential. And if you walk along one of these contour lines on a real hill, you're not going up or down. It's the same here. It takes zero effort, or no work, to move a charge along one of these lines.
So here we go. This slide really helps us flesh out our map. For that single positive charge, our electric mountain peak, the equipotential surfaces are these perfect concentric spheres centered right on it. Each sphere is like a different contour line, representing a different constant altitude. Just like that, we have a complete topographical map of our energy landscape.
So it's cool that we can see this landscape of potential energy exists. That's great. But what's the point? How do we actually use it? How do we capture all that potential and make it do something useful for us? This is the big engineering question, isn't it? If there's a height difference, a potential difference, between 2 points, there's a huge opportunity to store energy. It's just like how a dam stores the immense potential energy of water by holding it up high. We need to build an electric dam.
And here it is. This is our electric dam. It's called a capacitor. And honestly, for how important it is, it's an incredibly simple device. It's just two conductors, like metal plates, separated by an insulator. That's it. By piling positive charge on one plate and negative on the other, we create a nice steep potential difference, our electric hill, and we store energy in the process.
Now, the capacity of our electric dam has a name. It's called capacitance. It's really just a measure of how good a capacitor is at storing charge. Think of it this way. A capacitor with a really high capacitance can hold a ton of charge with just a small push, a small voltage. But a low capacitance device, you'd need a massive voltage to store that same amount of charge.
We measure capacitance in a unit called the farad. And here's a fun fact for you. 1 farad is an absolutely massive amount of capacitance. I mean, it's huge. In the real world, the capacitors inside your phone or your computer, they're usually measured in tiny fractions of a farad, like microfarads, that's millions, or even picofarads, which are trillions.
So if we want to store as much energy as possible, how do we do it? How do we design and engineer a capacitor to just hold a ridiculous amount of charge? How do we boost its capacitance? Well, the physics gives us 3 pretty simple rules to follow. First off, make the conductive plates bigger. More area basically means more room for the charge to hang out.
Second, you want to move those plates closer together. This really intensifies the electric field between them and jacks up the capacitance. And finally, there's a neat trick. You can slide a special insulating material, called a dielectric, right in between the plates, and that has the amazing effect of boosting the capacitor's storage ability even more. Now, in the world of electronics, you almost never find a capacitor working all by itself. They're team players. So what happens when we start hooking them up together in circuits? There are really two basic ways you can connect them. In series, which is one after the other like a train, or in parallel, side by side. And believe me, the results are completely different. When you put them in series, it's kind of like making the gap between the plates wider, which weirdly enough actually lowers the total capacitance. But when you put them in parallel, it's like making the plate area bigger, which as you'd expect, increases the total capacitance. And you can really see the difference clearly in these two diagrams. Over on the left, you've got the series connection, forcing the charge to go through one capacitor just to get to the next one. But on the right, that parallel connection gives the charge all these different paths to take, which effectively creates one giant capacitor. See? It's all about how you wire them up.
Okay, we've talked about landscapes and maps and circuits, but after all this theory, let's finally get to the real reason we build these things in the first place, the energy. This is the payoff.
And here it is. This simple formula tells you exactly how much energy is stored inside that capacitor. This number represents all the work, all the effort it took to push those charges up that electric hill. And now, that energy is just sitting there, stored, ready to be unleashed in an instant, to power everything from a camera flash to a life-saving defibrillator.
But here's the final mind-bending question. Where is this energy really? It's not physically inside the metal plates. As this quote tells us, it's stored in the electric field between the plates. The energy is in the landscape itself. All we did was build a device that could create a steep, contained piece of that landscape and capture the energy in its slope.
So by shifting how we see things from just simple forces to an entire landscape of energy, we can start to understand how to map, navigate, and truly harness the power of electricity. It opens up this whole new way of thinking about the invisible world that's all around us. So the only real question left is, now that you can see the landscape, what will you build on it?